The table here shows the observed and calculated values of the standard reduction potentials for the reduction of M+2 ions to their respective metals. It also shows the thermochemical data related to the transformation of the solid metal atoms to M2+ ions in solution. The calculated values of the potentials are those based on the standard enthalpies of formation of the +2 ions in an aqueous solution. The plots of the experimental and calculated values of the reduction potentials are shown in the figure. The curve in red corresponds to the observed values, while the one in black corresponds to the calculated values. The plots indicate that the experimental and calculated values are in close agreement with each other. The M+2 to M reduction potentials have enthalpic contributions from the terms in the equation shown here. The equation indicates that the magnitude of the reduction potential is governed by the values of three relatively large terms: the negative enthalpy of hydration of M2+ plus 840, the sum of the first and the second ionization enthalpies, and the smaller term enthalpy of atomization. The interplay between these three terms decides the value of the reduction potential. The irregularity in the variation of electrode potentials is due to the irregular variation of the ionization enthalpies and also the hydration energies of the divalent ions of these elements. All those elements with negative reduction potentials act as strong reducing agents and liberate hydrogen from dilute acids. For example, titanium 2+, vanadium 2+, and chromium 2+ ions act as strong reducing agents and liberate hydrogen from a dilute acid, as shown in the equations here. On the other hand, copper, with a positive reduction potential, does not liberate hydrogen from dilute acids. Thus, copper is inert towards non-oxidizing acids such as HCl, but reacts with oxidizing acids such as nitric acid and hot concentrated sulfuric acid, as shown here. The reason for this behavior is the high energy needed to transform solid copper to gaseous cupric ion, which is not exceeded by the hydration enthalpy of the ion. The general increase in the ionization energy sum is dominant in deciding the trend towards the less negative values of the M+2 to M reduction potentials. It is interesting to note that the values of the reduction potentials for manganese, nickel, and zinc are more negative than expected. The electrode potential values of manganese and zinc can be explained on the basis of the stability of the half-filled D subshell in Mn2+, and the completely filled D10 configuration in zinc 2+ ion. The stability is due to the maximization of the exchange energies between electrons of like spin. The electrode potential for nickel is related to the highest negative hydration enthalpy corresponding to its smaller radius. Now let us look at the trends in the standard electrode potentials of M+3 ions to M+2 ions. Not all the first row transition elements have the same pairs of stable oxidation states. The elements from vanadium to cobalt are chosen because they all have +2 and +3 states, for which reliable experimental data are available. The observed electrode potentials for these elements are shown in the table here. The lower value for vanadium is due to the stability of V2+, as it has a half-filled T2G level. Manganese has a higher electrode potential value than chromium and iron because of its very high third ionization energy, which is again due to the stability of the half-filled D5 configuration. The higher values for manganese and cobalt show that they are the strongest oxidizing agents in aqueous solutions. The comparatively low value for iron shows that the reduction of ferric ion to ferrous ion is less favorable, since ferric ion is extra stable due to the half-filled D5 configuration. Let's now look at the trends in stability of the higher oxidation states of these elements. The table here lists the stable halides of the 3D series of the transition elements. As can be seen from the table, titanium tetrahalides, vanadium pentafluoride, and chromium hexafluoride have the highest oxidation numbers. The highest oxidation state, +7, for manganese is not seen in simple halides, but MnO3F is known. Beyond manganese, no metal has a trihalide, with the exception of cobalt trifluoride and the trifluorides, trichlorides, and tribromides of iron. Fluorine stabilizes higher oxidation states either because of its higher lattice energy, as in the case of cobalt trifluoride, or higher bond enthalpy, as in the case of vanadium pentafluoride or chromium hexafluoride. Thus, vanadium pentafluoride is stable, while the other halides undergo hydrolysis to give oxohalides of the type VOX3. Fluorides are unstable in their lower oxidation states, and, therefore, chlorides, bromides, and iodides exist in +2 oxidation state, while fluorides do not. Copper, in +2 oxidation state, forms all the halides except iodides, because cupric ion oxidizes iodide to iodine. Copper +1 compounds, being unstable in aqueous solutions, undergo disproportionation to give stable cupric ion and copper, according to the equation shown here. The stability of Cu2+ ions rather than Cu+ ions is due to the higher negative hydration enthalpy of cupric ion than cuprous ion, which more than compensates for the second ionization enthalpy of copper. Now let's look at the higher oxidation states in oxides. The table here lists the oxides of the 3D series of elements. The highest oxidation number in an oxide coincides with the group number and is attained from scandium 3 oxide to manganese 7 oxide. No higher oxides are seen beyond manganese. For example, the only stable higher oxide formed by iron is iron 3 oxide. Although iron forms ferrates in alkali media in which iron is in +6 oxidation state, it readily decomposes into iron 3 oxide and oxygen. Apart from oxides, oxygen also stabilizes higher oxidation states in the form of oxocations. For example, vanadium 5 is stabilized as dioxovanadium 5 ion, vanadium 4 as oxovanadium 4 ion, and titanium 4 as oxotitanium 4 ion. Oxygen exceeds fluorine in its ability to stabilize higher oxidation states. Thus, the highest manganese fluoride is manganese tetrafluoride, while the highest oxide is manganese heptoxide. The ability of oxygen to form multiple bonds with metal atoms is responsible for its superiority over fluorine in stabilizing higher oxidation states. This ability can be clearly seen in the covalent oxide, manganese heptoxide. In this compound, each manganese atom is surrounded by 3 doubly bonded oxygen atoms, including an MnO-Mn bridge. Similarly, oxygen also forms double bonds in the tetrahedral MO4N- ions, known for vanadium 5, chromium 6, manganese 5, manganese 6 and manganese 7 ions.